A Bloom filter is a space-efficient probabilistic data structure used to test whether an element is a member of a set. The filter accepts elements during construction and answers membership queries with a known false positive rate, but zero false negatives. Memory overhead remains constant regardless of set cardinality. The implementation maintains an internal bit array of configurable length and applies multiple independent hash functions to each inserted element. Filter construction begins by specifying the expected number of elements and desired false positive probability. The system calculates optimal bit array size using the formula m equals -n times log 2 of p squared divided by ln of 2. The number of hash functions k is computed as m divided by n times ln of 2. These parameters determine memory footprint and collision behavior during subsequent operations. Insertion operations accept an element and apply all k hash functions to derive bit positions within the array. Each derived position is set to 1 regardless of previous state. Multiple insertions of identical elements are idempotent. The insertion operation completes in constant time proportional to the number of hash functions. No removal mechanism exists in standard Bloom filters, as individual bit positions cannot be safely cleared without affecting other elements. Query operations accept an element and apply the same k hash functions to compute bit positions. The filter returns true only if all k positions contain a 1 value. A false positive result occurs when hash collisions cause all positions to be set despite the element never being inserted. The actual false positive rate approaches the theoretical probability as the filter approaches saturation. Query execution is also constant time relative to k. False positive rate degradation occurs predictably as insertion count approaches the filter's capacity. The actual probability is approximated by the formula 1 minus e to the negative k times n divided by m raised to the power k. Monitoring insertion count against expected capacity allows clients to estimate current false positive behavior. When degradation reaches unacceptable thresholds, the implementation triggers filter regeneration rather than attempting in-place modification. Counting Bloom filters extend the standard variant by replacing individual bits with small counters. Each counter increments on insertion and decrements on removal. Removal safety is achieved through counter state preservation. A counter overflow event occurs if insertion frequency exceeds counter bit width. The implementation configures counter size based on expected insertion patterns. Decrement operations on zero-valued counters are treated as no operations without error signaling. Scalable Bloom filters address capacity limitations through multi-stage filter chains. When a filter reaches a target saturation level, a new filter is created with larger capacity and appended to the chain. Query operations examine each filter in sequence until a definitive answer is found. The cumulative false positive rate is computed as the product of individual filter false positive rates. This approach allows unbounded set growth with logarithmic memory scaling. Hash function selection significantly impacts filter performance and false positive behavior. Cryptographic hash functions are generally avoided due to computational overhead. The implementation employs fast non-cryptographic functions such as murmur or Roman 20 hash. Multiple independent hash values are derived from a single initial hash output through transformation functions rather than calling distinct algorithms. This approach preserves statistical independence while minimizing computational cost during insertion and query operations. Decay protocols manage filter staleness in scenarios where set membership changes over time. Age-based decay assigns timestamps to filter creation and compares current time against configurable staleness thresholds. When a filter exceeds maximum age, query operations return a stale indicator rather than a definitive answer. Cascade decay strategies simultaneously age all filters in a chain proportionally. Applications configure decay parameters based on acceptable staleness windows for their use cases. Periodic reset operations clear filter state and reinitialize bit arrays. Reset triggers are determined by elapsed time or insertion count thresholds. The implementation schedules reset operations asynchronously to avoid query latency impact. During reset transition, queries may reference either the old filter or new filter depending on timing. Clients implementing reset protocols must tolerate temporary false negative responses until all filters complete reinitialization and synchronization occurs. Serialization of filter state encodes the bit array and configuration parameters into a binary format. The serialized representation includes bit array contents, hash function seeds, element count metadata, and creation timestamp. Deserialization reconstructs the filter to its previous state assuming no intermediate modifications. The format supports optional compression for persistence in storage systems. Version headers enable forward compatibility when implementation changes occur. Distributed Bloom filters coordinate across multiple nodes through filter replication or aggregation. Replication maintains identical copies on separate nodes for query locality. Aggregation combines filter responses from multiple nodes, using logical or operations on bit arrays. Aggregated filters represent the union of all individual sets with increased false positive rates. Consistency considerations require either eventual consistency, acceptance, or synchronization protocols before responding to queries. Error handling in query operations addresses several failure modes. Hash function failures are treated as transient and trigger exponential back-off retry logic. Corrupted bit array states are detected through checksums and trigger immediate filter regeneration. Saturation detection occurs when false positive rates exceed configurable bounds and signals applications to initiate remediation. Resource exhaustion during allocation returns explicit error codes rather than failing silently. Configuration parameters control filter behavior and performance characteristics. The expected element count parameter determines initial bit array sizing. The target false positive probability parameter influences hash function count and memory allocation. The decay threshold specifies maximum acceptable age in seconds. The saturation trigger sets the false positive rate ceiling that initiates regeneration. The hash seed provides deterministic behavior across filter instantiations. Configuration changes apply only to newly constructed filters. Performance characteristics remain consistent across filter lifecycle stages until saturation approaches. Insertion and query operations execute in constant time O of k regardless of set cardinality. Memory consumption stays fixed at mbits plus constant metadata overhead. Cache efficiency is high due to sequential bit array access patterns. As saturation increases, false positive rates rise predictably according to theoretical models. Real-world performance degradation typically becomes noticeable before false positive rate reaches critical levels. Lifecycle management best practices include monitoring insertion count against capacity, scheduling preemptive regeneration before saturation, maintaining audit logs of filter state transitions, and validating hash function behavior through statistical tests. Applications should configure appropriate false positive thresholds based on downstream impact assessment. Decay protocols require clock synchronization in distributed deployments. Regular testing of serialization and deserialization paths prevents data loss during recovery operations.